Today, I'll be discussing the analysis of spatially orthotropic laminates. Specifically, I will discuss the bending behavior of spatially orthotropic laminates. Here we know that for spatially orthotropic laminates, the bending stretching coupling coefficient, which is Bij, uh, and also the bending twisting coefficients, particularly these two coefficients T16 and D26 are 0. An example of this specially orthotrophic laminates uh, are the cross ply laminates, 090 laminates, but symmetric. So cross ply and symmetric. So symmetric should be there. Otherwise, this Bij won't be 0. So symmetric cross ply laminates will have this behavior. So here I want to mention that the most practical laminate sequence may not uh, be especially orthotrophic laminates, but this is a good starting point to understand the behavior, bending behavior of plates. Because in this particular case, we will get a analytical solution, and we'll see how uh, the result can be interpreted. So for this kind of laminates, there are okay. So before discussing this Navier method and Levy method, let me pull out a schematic diagram to show what we are going to discuss in this lecture. So there will be a plate. We know that we are uh, adopting this coordinate system where x, y, and z is shown in this way. And there is a transverse load qxy, and there won't be any other loads because we will be discussing or interested in the transverse uh, uh, loading case. The stress and deformation due to transverse load, and this plate will be consisted of a number of layers, 1 to n, and here we are considering uh, a layer sequence for which we get especially orthotropic behavior. So with this, let me again go back to the PDF which I shared with you. So to solve this specially orthotropic laminates, the bending behavior, we have two method of solution. One is Navier method, another is Levy method. So Navier method is particularly applicable to rectangular laminate with all four edges simply supported. Okay, all four edges simply supported. And the Levy method is applicable to to rectangular plates with two opposite edges simply supported, and the remaining two edges can have any combination of these three boundary conditions: free, simply support, or fixed. So it can be like two simply supported edges and another two can be clamped, or can be clamped and simply supported, or the other two can be free, simply supported, or any combination like that. So for this particular boundary conditions, the Levy solutions can be applicable. So with this, using these two methods, we'll be trying to solve the deflection and stresses due to some transverse load. That's called the bending behavior. And in subsequent lectures, we'll be discussing this other two cases, and that is frequency analysis, the natural vibration analysis, and the buckling analysis. All right, so now let us see what is the governing differential equation for our case. So we already from our previous lecture, we have seen that for especially orthotropic laminates, the out of plane behavior, uh, the rounding differential equation reduced to a very simple form like this. Here we are using a static case, so that's why no dynamic terms, no time derivatives involved, and then no in-plane forces. So that meant like the nonlinear terms and zero is also not there. So we are living with this term. So this equation we have to solve now. So now for the Navier solution, we are uh, trying to solve this problem for simply supported all four edges simply supported case, and the boundary conditions are uh, this. So for simply supported is the uh, transverse deflection should be zero, and the uh, moment reaction is zero because it is free to rotate the edges. So the moment reactions will be zero. Let me go to the next page to show a schematic of the boundary conditions. So here you can see this is my x is equal to 0 line. Sorry, this is y-axis is your x equal to 0 line, and this is x-axis is your y equal to 0 line, and that's the x-axis direction is the length is a, and along the y-axis we have the width b, and now we can see all four edges there are deflection 0, w is 0, and then at y is equal to 0 and y equal to b we have my 0, and this is the moment m axis at x is equal to 0 and x is equal to a should be 0. So these are the boundary conditions we need to satisfy for the Navier method, and we need to see what is the moment relation with respect to the deflection w. This is what it is written again. It was taken from the earlier class notes which I have sent to you. So with this, now let us see how we can proceed. All right. So for in the Navier solution, what is done is this displacement w is expanded in a double trigonometric Fourier series, and there will be unknown coefficients to each double sine series, and uh, for the present case, the boundary condition are okay. So the sine series we will choose so that this deflection W will be satisfying the boundary conditions. So for this case, you can see we can assume a solution in this form, which is already satisfying the boundary condition given in the previous page. So you can, if you carefully see that at all four edges, we have both deflection and moment boundary conditions, and this solution, assumed solution, will be satisfying all this. And here you have one undetermined coefficients in each term, Wmn, which we have to find out, and we'll see how we can find out. And here alpha is m pi by a, beta is n pi by b. So this is how this double sine series is defined. Now the load qxy is also expanded in double trigonometric series. So we know that any function can be expressed in a Fourier series. With that sense, the qxy is also expressed in a double Fourier series. here in sign series. And the QMN, because QXY is known, so that's why you can find out QMN. So QMN is not unknown. Like earlier we expressed the displacement where WMN is not known yet, but QMN is known because we know the loading condition for which we are trying to solve this problem. And this QMN coefficient can be obtained using this expression, using the Fourier series relation. So once we expressed both Qxy and Wxy, so now we can put this expressions in the governing differential equation, and you will see that leads to this expression. If we bring everything to the left side, you will get the expressions in this form. And this is also in a series form, but we know that this equation must hold for each every point x and y in the domain of the plate. So to satisfy that, the expression which is in the curly bracket, so this expression should be 0. It has to be 0 to satisfy this relation in for every x and y. So with setting this expression to 0, we'll see that Wmn can be found out as Qmn by Dmn, where Dmn is this term. Dmn is expressed as this. Here S we have defined as the aspect ratio A by B, and it is depending on the coefficients D11, so elastic coefficients D11, D2, D12, D66, and the bending stiffnesses. So these D values, and then AM and N and S. Okay. So we know that now once QMN is known, and we know the D matrix of a particular laminate sequence, then for each M and N, and a given plate geometry where AB is defined, then you can find for each M and N what will be the D, and then accordingly the WMN can be found out. So that this one I will show you how this will work using a demonstration in the MATLAB. So that code already I have said, but I will explain what is done there in that code. So then once WMN is known, so we can put that in the displacement expression. So now you know what is the deformation of the plate due to the load QXY. So let us see what will be the expression Q of QMN for different kind of loading. So here we can take few load cases. For first can be the simpler one, which is the sinusoidally distributed transverse load. So if the load is itself is sinusoidally distributed, then we can see the one sign series, only single term of the sign series will satisfy that load equation, and then Q0 is constant, and that will be equal to QMN. So therefore M and N is 1. So now we'll get the solution also in the same way. So you will have only one term in the sign series, and where D11, this one can be calculated based on the laminate sequence and the geometry of the plate. So this is a closed form solution. Now, for other cases, we will not get closed form solution, we will get series solution, but we can take sufficient terms for the convergence. For example, if the load is uniformly distributed, then the Qxy is constant, so it is Q0. Then the Qmn, capital Qmn, using for that integration, that form coefficient, how to find the coefficient. If we put this Qxy equal to Q0, we'll see that the capital Qmn will turns out to be this expression, and here m and n will be odd terms. So that's also we have to make a note, because for some cases the m and n will be just odd, leaving the even terms. For even terms, the coefficients at 0. So in the same direction, we'll see that the deflection solution, the W, also will have the even terms 0. So whatever terms we'll get in the Qmn, we'll get the similar terms in Wmn, because Wmn is dependent on Qmn as per our solution we got earlier. And now if we have a point load at, let us say, at x0, y0, then the coefficients Qmn can be obtained like this. So this depends on the x0 and y0 position. And mn starts from 1, and it takes every terms. So 1, 2, 3, 4, like that. So you don't have any even term 0 in this case. So you have to take every term for the solution. All right. So now let us say we know Qmn, and then we'll be able to find out the displacement term completely. And then once we know the displacement Wxy, then how we can find the stress. So to compute stress components, we can first find the bending moments, or you can use direct relations. We have already obtained those solutions in the first lecture notes. I have given you the expression, the stress and the displacement relation. So we can again discuss this here. So mx, the moment components in the expression which we have discussed in this node also in the beginning when I discussed the boundary condition, you can see that page. So there we can put the expression of the displacement W, and we will see that we'll get some series solution in this form. And then for the stress also, we can either we can directly get this relation. So here this is the stress strain relation. You can see this this right hand term is related to strain. So let me see, show you again where from we are getting this. Okay, this is my first lecture notes, and this is page 4. Yeah, if you see the page 4, I've shown you this relation, how the stress and strain is related, and this is the epsilon x, y, and gamma xy. And for this case, actually because we are taking a symmetric cross ply laminate, so the the mid plane actually is coinciding with the neutral plane, because if the laminate is symmetric, then the neutral plane actually coincides with the mid plane, and therefore the mid plane strains or the displacements are zero. So that's why u0 v0 for this case will be 0. So so you can see for the strain expression, this term will be 0. So you'll have only this z into kx, ky, and kxy, the curvature term. And so if we just take this curvature term for the strain, so you will see that it will be uh, we'll get the relation as sigma equal to minus z q into the curvature term. Sorry, minus will get uh, if we just take the minus out from here. So then this minus can go to this z, because each term here having some minus sign. So that's what it is done in that in our the present PDF which I have was discussing. So now you can see what is this, and here this minus actually is a mistake, typo mistake. So here this minus z, and then this is the curvature terms, and then these is the matrix. And for this specially orthotrophic case, we will not have these terms. So these terms will be 0, that 1, 6 and 2, 6 terms. All right, so now we can put the displacement expression in terms of Fourier series, and then we'll see that we'll get this relation. All right, so now we can calculate what will be the stress components at different positions x, y, z, and we note for this case that the maximum normal stress will be occurring at a by 2, b by 2, and h by 2, the sigma x and sigma y, and the shear stress will be maximum at the corner a b a comma b comma minus h by 2. So this is one corner, and it will be uh, same as the magnitude will be same at other three corners also. So now let us see what are the numbers actually for a particular case. So to express these quantities in a non-dimensional form, we adopted this form here, and this is actually this notes mostly I have followed Jane Reddy, the book called uh, Analysis of Laminated Composite Plates. So from there we will get more details on this, but I have just taken the uh, important pieces and written in this document for your help. So now I'm just showing you this solution for three loading cases, and mostly I will try to demonstrate this too using a MATLAB code, uniformly distributed load and the central point load. And here the W is okay. This one also there is a little mistake here. In fact, that mistake was there in the book when I tried to calculate using MATLAB. I have seen that this would be at the middle, because anyway that this uh, um, W0 comma 0 is 0. So this term anyway will become 0 if we have if we take this corner point. So actually it should be the middle. So this is W A by 2 comma B by 2. It's a middle point. And then we have to normalize this non-dimensional to get this non-dimensional number using this parameters. And to get a reasonable like number, so 10 square also is multiplied, because that way you will get a number in close to 1, you can say. And the stress is also normalized with respect to the midpoint of the plate and at the extreme topmost layer, okay, h by 2. So at that point you will have the maximum normal stress. So it is at the middle point and at the normal at the topmost fiber uh, of the laminate, okay. And the shear stress is normalized with respect to the value we get at the corner AB and at the bottommost fiber or bottommost layer minus h by 2. And we can see there are two types of laminate sequence taken in this case in the table. One is only one layer, which is 0 degree, and other is 3 layers, 0, 90 and 0. And for each of these layers, 3 layers, the laminate thickness should be equal. Okay, so sorry, the thickness of the laminate should be equal. All right, so here the SSL denotes your sinusoidal load, which is a closed form solution, and for UDL is uniformly distributed load, and CPL is central point load. And you can see for this case we don't have any numbers in the parenthesis because it's a closed form, but for UDL we have to have the sufficient numbers to get a converse solution. So here 19 almost give a converse solution. For point load we need to have more numbers, so we need 49 terms. So the number of terms also indicated here. And then material properties, here we have taken this this material properties. All the stiffness coefficients are compared with E2, Young's modulus in the two directions. So E1 is 25 times E2, Z12 is 0.5 times E2, and this is a non-dimensional term, so 0.25% ratio. And all laminates are of the same total thickness. So 0 degree, if it is of H, then this also will have total thickness H. So that means these 3 layers will have H by 3, H by 3 and H by 3. All right, with this now let us say how this Navier solution can be implemented in a MATLAB code, and we can generate these numbers which I am showing here. So now I have opened this Navier solution for the uniformly distributed load case. This I have already shared with you. So here we are taking 19 terms because that's what mentioned there, and then the number of terms for n and m should be same. And then let us say this is a square plate, so that's what it is mentioned. So this is for square plate, square laminate. All right, so for square plate, so that's why here one I have taken, but you can take 2, 2, 3, 4, sorry, 3 3 or 4 4, that doesn't make difference because the results are normalized. That's why I have taken E2 1, but you can take any, you can put any value, it will work. Q is 1, we can take any value, that also will work. So we can, or you can because the code is with you, you can uh, check by changing these values. And then there is a AVD, there is a sub function, AVD matrix and Q bar. So AVD matrix is needed for deflection calculation, and then Q bar is needed for stress calculation. So Q bar, and I want the top layer Q matrix, the Q bar matrix for the top layer, because the stresses are calculated at the topmost fiber, and it is symmetric, so that's why the top and bottom Q bar will be same. So because this laminate is symmetric. So this sub function, let us see what it is. Let me make it a little bigger. In your this will be shared in YouTube platform. So maybe this font, it may not be visible that much, but I think because the codes are with you, so you can very well do on your own and see how the code is running. So I'm just giving a brief overview of what is this code. Okay, this is the SAF function, and here first the mat is the material properties, lam is the laminate sequence. Here 0 90 0 is taken, and for the theta top is defined as the 0 degree layer. So again, you can make this code better, but I have just spent a little time to get the numbers out. So the code may not be written nicely, but you can modify, improve the code. That's always there. And then this ABD matrix calculation is implemented here. How the ABD matrix is calculated, you can see uh, the notes which already I have shared, or even I think if you search internet you may find it, but you can better you do on your own some ABD matrix coding. So this is done by me in this way. And then yeah, so this after ABD matrix, I just find out again the Q bar matrix at the top layer, theta top. So this is the Q bar top, and this is your ABD matrix, and that's what the output of this function. So D and Q bar top, so that goes here, and after that I again read these values D's, and then X Y is symbolic. After that, I initiate sigma bar and sigma 2 bars. 2 bar is taken here because you know that the tau xy is calculated minus h by 2, and at position a comma b comma minus h by 2. So the position of these two, sigma normal stress and the shear stress difference, that's different. That's why I have taken mm, uh, 2 sigma bar. So in this case also I'll calculate 3 components. For sigma 2 bar also I'll calculate 3 components. But from the first component, I'll take only first 2 normal stress components. And for the second 3 components, I'll only see what is the third component, which is the shear stress. Okay. And then there's odd terms taken here, leaving the even terms, and then alpha, beta, qmn. This is udl, qmn is defined like this. Then dmn is defined like this. Then wmn is defined in this way. And then function fw is defined here because this is a symbolic function. Xy will be symbolic. Then we can use the mid point deflection as this, a by 2, a by 2, but I think it's b by 2 also, because a equal to b, so it should be b by 2. A minor mistake here, but I think this is square plate, that's why it's fine. Let me just change it b by 2. And then w bar is, because it's a series solution, it will take all uh, for each m and n, it will find w bar and then it will be added. Okay, this is a for loop going, so that's why every time will be added to get the final number, this summed up number. And then I'm defining, because this is needed for the double partial derivative of the w with respect to xx, yy, and xyy. This is for needed for the stress calculation. And then I'm defining them as a function, and then fx as yy and xy, and then I'm calculating the sigma mid and then sigma bar. The sigma mid is the stress we want, but then we have to um, sum up. So the next line is for the summing up this, and the normalization is done here. And this is also sorry, this should not be mid, this is actually the corner. So here you can rename it to sigma underscore corner, and then here also you can put sigma corner, because this is evaluated at a comma p, and then normalized here. So this sigma 2 bar will give you the um, uh, the shear stress component, and sigma bar will give you the normal stress. All right, so let us run this and see what we get. I'm waiting for the results to come out. I don't know why it is taking this much time, but earlier I've seen it doesn't take that much time. Okay, so it's done. You can see, let me go back and see what are the values. Okay, so this is 0, 90, 0, and this is the stress 0.6, sorry, the deflection normalized 0.6660. What I get is 0.6660, and then the sigma bar component here, this is for normal stress, and you can see for the normal stress 0.807, 0.0306, 0.807, 0.0306, and for the shear stress I have to take sigma 2 bar, and this is 0.425, and here this is 0.425, so it's exactly matching. So the same thing can be done for the CPL, central point load. Only thing what you have to change is the QMN. So the code is same. Only thing we have to take more numbers, 49, and then there is nothing changes in this code apart from this one, QMN. So this QMN we have to change. All right, so if you run for this case also, you'll see we get exact matches. So I leave you to run and check how close you get the numbers. And after that, okay, in next lecture, I will show you how we can use Levy solution for uh, for solving other boundary conditions apart from all four is simply supported. So that I will discuss in your next lecture.